So now when we go back to our buckling now, okay, so I'm going to copy this, or I'm going to copy the whole thing. Yeah. Okay, I'm going to back to buckling. Sorry about this. Okay. So now coming back to buckling, where are we now? Okay. So we are going to focus on at point Q, you have moment MQ. Okay, at point Q is equal to minus PY. Why minus? Because you have a negative, you have a clockwise rotation over there. Okay. So from here, now we are going to apply the elastic curve. So we remember M at point Q is equal to minus PY, and this is equal to EI d squared Y over dx squared. Okay, so this is where we apply the elastic curve. So from here, we are going to have EI d squared Y over dx squared plus by PY, the whole thing is equal to 0. Okay. Now, what we are trying to achieve here, okay, let me recall what are we trying to do, okay? We are trying to prove, okay, so I write down here. Sometimes it's so much in the lecture, we don't know what we are trying to do. What we want to achieve. Okay. We want to prove that PCR, the critical load, okay, the critical load is equal to pi squared EI over L squared. And we also want to know that the critical stress is pi squared E over L over R squared. Okay. This is what we are trying to achieve. Okay. But now we are in this expression over here. Okay. We're in this expression over here. So the guy that invented this equation, his name is Euler. Okay. L-E-U-L-E-R. Sometimes I think I have to change the pronunciation of my name to Euler because it's also. Okay. So Euler comes to this where he has EI d squared y over dx squared plus by py is equal to 0. Okay. You all have to imagine, imagine such that he has not come up with the expression where the critical load is equal to pi squared EI over L squared. Yes, no, that is the end product. Are we clear? Right? So you have an expression over here that you have to calculate deflection as a function of P. But on the right-hand side, what you want to know is what? P. On the left-hand side, when you solve, what do you get? Deflection, am I right? Not the load, okay? So during those days in the 1800s or even earlier, what we do not have? What we do not have in the 1800s? We don't have computer, we don't have internet, we don't have what? Television. Television is a source of trouble, yes or no? After television, nothing great is invented. Okay? So what he did is, okay, I have to solve this. Okay, that's what he told himself. I have to solve this. Okay. So to solve this, okay, he wrote the equation out as d squared y over dx squared plus by p over ei
y, the whole thing is equal to 0. Seen this before? You don't need to integrate 2 times. Is it integrate or differentiate? Yeah, integrate, right? Right? He does not need to, it's a second order differential equation, okay? So let me quickly recall about our second order differential equation. If we look at the parent function, we can write a d squared y over dx squared plus by b dy by dx plus by cy, the whole thing will be equal to 0. Okay, and we know that the roots, for this case, to find the roots, we know is minus b plus minus square root b squared minus 4ac divided by what? Divided by 2a. Okay. Then we're going to let alpha is equal to b over 2a. And we're going to let beta to be equal to b squared minus 4ac divided by 2a. Now, what we know over here, looking at this expression over here, right? Looking at this expression over here, we do know that b is equal to what? B is equal to 0. So what we have now, when b equal to 0, we're going to have complex conjugate roots. Okay, we know that we are going to get a complex conjugate roots. So therefore, our general solution will be in a form that as y as a function of x is equal to e minus alpha x. And then we have C1 sine, I'm going to call this omega x plus by C2 cos omega x. Okay. Now, what we're going to take note that beta is equal to square root b squared minus 4ac over 2a. And from our equation over here, we know that what? We know that a is equal to what? A is equal to 1. Okay, so therefore, beta, and not just a is equal to 1, b is equal to 0. Yes or no? So therefore, this will be equal to square root minus 4 over 2, or minus 4c over 2. Okay, so we are going to we cannot square root a negative sign. Okay, so we're going to let omega, which is equal to what? So this will be equal to c, because square root of 4 is equal to 2. Okay, so from here, we know that y as a function of x is equal to, so e to power 0 is equal to 1. Okay, so now this is equal to c1, square root is missing. Okay, c1 sine square root cx plus by c2 cos square root cx. And then we are going to let, okay, we're going to let P Now, the next thing that we're going to do is we're going to let, now this is small p, okay? We're going to let p, okay, we're going to let small p squared, which is equal to what? Small p squared, which is equal to c, okay? Small p, okay, not big P. Now, the P that I've drawn earlier, this is a capital P, okay? And then this is a small p, okay? So they're not the same. So therefore, we have y as a function of x is equal to c1 sine small p x plus by c2 cos p small p x. It's not capital P, it's small p, okay? So note that our small p is in fact equal to the square root capital P over EI. Okay, I will put this in first. Okay. So that's what. So you can see one is a small letter, one is capital letter. Now, the next thing we're going to do is we're going to impose our boundary condition. So if we go to our boundary condition yesterday, where is our boundary condition yesterday? Right. So we have our boundary condition over here. Okay, so this is yesterday's notes. Yes. So what we do over here, we call this equal, this is equal to, we just name this equal to small p. Okay, it's just a label, okay? So from here, so that I don't need to always write square root big P over here, but later on, we have to put it back, okay? So from here, right, we know our boundary condition, okay? So we're going to substitute our boundary condition number 1 that states that when x is equal to 0, y of 0 is also equal to 0. Okay, so we're going to substitute that. So this is our equation number, yeah, I can't remember now. I'm going to call it 7. Okay, so from here, we know that what? We know that C2, right? From here, we know that C, is it C2? We know that C2 from here, we know that C2. So if this is 0, C1 multiplied by 0 plus by C2, which is 0 cos of anything that is 0 is equal to 1. Okay, so therefore, C2 is equal to 0. Okay, so we have an expression y as a function of x is equal to C1. Okay, C1 sine px. Okay, sine px. And then the next thing that we're going to do, like before, we're going to substitute boundary condition number 2 that states that when x is equal to a distance of L, right, y is equal to 0. Okay, so when this is the case, we know that I'm going to call this our equation 7a. Okay. Okay. And we're going to substitute into equation 7a. So from here, when we substitute in, we have y as a function of L equal to C1 sine small p multiplied by L. And we know that this is also equal to what? This is equal to 0. Okay. Now remember what I told you before. Euler is not interested in detection. Right? What is Euler interested in? Okay. So Euler is not interested in. So we are not interested in. I know this is very abstract, okay? We know that I am not what? This is what we desire. This is what we want to find out. Okay. So in order to do that, okay, he asked himself in what condition in what condition where C1 sine PL will be equal to 0 is true, right? So he realized that the conditions are when PL is equal to n pi, because sine of pi is equal to what? 0. 1 pi is 0, 2 pi is 0, 3 pi is 0, 4 pi is 0. So he believed that n can be equal to 1, 2, 3, and 4. Okay, I'll see you guys on Friday.